Hello everyone, my name is Shehzad Ahmed and I am currently a postdoctoral researcher at Radar Computing Lab, Hanyang University, South Korea. And I would like to thank you all for being here at my presentation titled as Human Activity Recognition using FMCW Radar and Deep Learning. So here is the quick outline of my presentation. I will start with the introduction to human activity recognition. Then I will discuss the available sensors for human activity recognition. Then I will briefly introduce FMCW radar. Then I will move to methodology, which includes the signal preprocessing and then range Doppler and range FFT extraction from FMCW radar and then deep learning model used in this study. Then I will explain the experimental setup and results. Finally, I will conclude the paper and mention the limitations as well as the further work associated with this paper. So, human activity recognition. The purpose of human activity recognition is to automatically identify a user's behavior for several different applications. For example, the human activity recognition can enable a wide range of applications such as healthcare, elderly care, smart environment, and hazard prevention. In particular, healthcare industry can be a direct beneficiary of human activity recognition. Uh, uh, Currently, with the better healthcare facilities, the life expectancy in many countries, specifically the developed countries, is increasing. And according to WHO, the population aged over 65 years will soon surpass the population of children. And elderly people normally need 24/7 hospitalization or nursing, which is not feasible with human resources. Consequently, activity recognition can be a key component for pervasive healthcare applications. So, the available sensors for human activity recognition. So based on the type of sensor used, human activity recognition can be classified into two classes. That is, first one is the wireless sensor based. For example, the first one is wearable sensor based. For example, accelerometer, gyroscope, or ECG electrode. And the second one is wireless sensor based. For example, camera or the radio sensors. Radio sensors such as radar are widely used for activity recognition. So normally, first we perform an activity, capture it using any of the available sensor, then denoise the capture signal, and then we perform classification. So here I would like to mention that radar has quite few benefit over the other wireless sensor, that is camera. For example, radar is not affected by the environmental conditions such as dust or low or high light condition, whereas radar doesn't have a privacy issue associated with it. With However, based on the application or the environment being used, any suitable sensor can be used. So FMCW radar has quite been around for a while, and we have seen a lot of industrial applications as well. Most of us might be aware of the Google Soli camera used in Pixel 4 smartphone. That is also an FMCW radar based. And we have also seen FMCW radar in adaptive cruise controls and in children vital sign detection and gait analysis. So not only the automotive application, but the human computer interface design as well as healthcare applications are being made using FMCW radar. So a lot of studies have been proposed for human activity recognition with FMCW radar. For example, we have seen residual neural network based activity recognition. Then there is another recent example of features driven LSTM for activity recognition. The aim of our study is to recognize the transitional activities, that is when the person tries to get up or it tries to sit down or tries to get out of the bed. These kind of activities are being included in our paper. So, proposed methodology for human activity recognition. So we capture this is the overall methodology used in this paper. We start with the capturing the raw data, then clutter reduction is performed, and then we perform the fast Fourier transform to extract the distance and as well as velocity. Uh, I will explain later how that is being performed, and then we convert the data into images which are fed to a deep learning model for training, testing, and then evaluation. So FMCW radar signal overview. So as we can see in this figure, FMCW radar transmits a signal having a bandwidth whose frequency changes with certain time changes within a certain time period t. It starts from a certain bandwidth and then goes up to a maximum limit bandwidth b. So as we can see, that transmitted signal has increasing frequency trend, and similarly the receiving frequency will also have the similar kind of trend. And when we differentiate, when we mix the received signal with a copy of transmitted signal, we get an intermediate frequency signal known as XIF of t, which contains the target's information. So after receiving the intermediate frequency signal, the next step is the range FFT and Doppler FFT extraction. So range FFT, so the transmitted frames are arranged in a matrix as shown in this figure, and then we take a FFT across each chips. So FFT across each chips resolves the target into range time map. So after that, if we take another FFT, if we have multiple chips in the frame and we take FFT along each chips, we can get the frequency or Doppler frequency or the velocity. So from the first FFT we get range time map or range FFT, and from second FFT we get the range Doppler map. So these two images can be used to train a deep learning model, because for each of the activity the pattern of these images will be different. So after getting the output from the range and Doppler FFT, the next step is to compute the performed activity, or we can say to classify the performed activity. So for that purpose, currently we use a simple 3-layered deep learning model, that is convolutional neural network model. The input to the model was 100 into 150 RGB image, and currently we only use the range FFT as to show the preliminary results. So we trained using RTX 2060 GPU, and for data collection 3 human volunteers were involved, and we captured 2100 samples for these activities. So experimental setup and results. So we used IWR 6843 FMCW radar designed by Texas Instrument. The radar has multiple antennas, whereas for currently we only use one transmitter and one receiver, and the starting frequency of the chip was 60.25 gigahertz, and then it spanned over a bandwidth of 3.75 gigahertz, and there were 128 chips per frame with 20 frames per second of frame repetition interval. So as I mentioned earlier, we tried to perform classification of transition activities. For those activities were stand to sit on a chair or a bed, sit to stand to then move forward, move away from radar, pick up something from ground, and move left and right randomly, or stay still. So for example, if an elderly person tries to get out of the bed, there is a possibility that fall could happen. And mostly the elderly person or the person in the hospital are not allowed to get out of the bed any without any without supervision of any medical personnel, but still they try to attempt. So the radar can automatically detect that person is getting out of the bed or is standing up from the chair, and can generate an associated alarm. So this was the experimental setup. Here we installed the FMCW radar on the front, and the data was captured on the host computer. So activity transition analysis. So the activity was performed for 5 seconds in front of radar. So we can see there are transitions for in the range FFT, or we can say the distance time map. Stand to state, whereas sit to stand have totally opposite kind of pattern. And we can see in the first graph, when the human volunteer was sitting, the pattern is different. When it generates uh, when the transition happens, the pattern changes, and then after standing, the pattern is different. Similarly is the case for sit to stand as well. So these kind of transitions are being recognized using deep learning model. Here are the distance versus time graphs of each of the activity performed. Here x-axis represents the time, whereas y-axis represents the distance. So stand to sit, sit to stand, whereas if we move towards the radar, distance keeps on reducing, whereas if we go away from radar, this distance keeps on increasing. So picking up on something creates a little bit deflection in the distance graph, whereas moving left to right shows kind of changing pattern, and stay still, there was a constant graph. So as I explained earlier, there were 3 participants and 100 sample in total for each activity. So 3 participants, 100 samples in total for each activity, and overall 95% accuracy was achieved. So it was seen that activity of picking up something from ground showed a little bit of less accuracy. Limitation and further work. Right now the accuracy was quantified in discrete way. We only performed these activities and there was no comparison with the other random movements. So activity patterns can easily get mixed with other similar movement. For example, just moving one step towards the radar could also be mixed as getting up from the chair or bed. So in order to cope with these kind of problems, we are trying to incorporate the other FMCW details, such as the Doppler velocity and the horizontal and vertical angles. So by combining the changing distance, changing velocity, as well as azimuth and elevation of humans, we can extract a rich features vector which can contribute significantly to for the robustness of the proposed algorithm. Thank you so much for your kind attention. Please feel free to contact me.